So we were recently doing percentage yield. We are already done with percentage purity. At this point, the specific portion of the chapter ends 6.3. Now 6.4 is about volume of gases, which I did previously. You already know about the molar volume or how the volume conversions work. So you already know all of this stuff. You know how we put in the masses or the volumes or the number of particles. Okay. And you also know that how we convert the formula ratio, formula steps, the whole footbridge method to convert this. Now, this brings us to actually the last topic of the chapter, which is solution chemistry. So we are supposed to discuss solutions in this topic, right? So I hope when I say the word solution or when I talk about the solute or the solvent, you do understand what these words mean. Solution is actually a combination of solute and solvent. Solute is something that we dissolve in. Solvent is something that dissolves the other stuff, of course, which is usually in bigger amount most of the time. So what we're going to do is that we are going to do this on a separate piece of paper on whiteboard, and then we'll get to the questions. When you see solutions, we are going to work on concentration questions. And then another part of the same topic would be titration, acid-base titration. And following this whole thing, we'll wind up the whole chapter. So getting towards solutions, so when I say the word concentration, let's start from the very basic. I am actually talking and trying to talk about amount of solute in a solution. Okay, I am specifically using just the two words solute and solution. I'm not using the word solvent because the amount of solvent is not important in here. The concentration really depends upon the amount of solute in comparison to the whole solution, not the solvent. And they also do not work on the basic mathematic principles. So don't try to simply add up the amount of solute to the solvent to get the total amount of the solution. That's not how it works. This is the very basic that a student should keep in mind. Now, when I say the word concentration, I actually divide it into two categories. So the first one is mass concentration. I'm starting from the mass concentration type because mass concentration is a bit easier to work with. As the name suggests, we are going to go with the simple units of grams over decimeter cube. Now, whichever unit I put up top, this is the unit that works for solute, and whichever unit I put as the denominator, which in this case is decimeter cube, it works for the whole solution. So mass concentration is pretty simple. The formula is really easy. As numerator, we have the mass of the solvent, solute, which we'll take in the standard units of grams. We're going to divide it by volume of solution. And that's why I was talking about why I'm choosing just the two words solute and solution, because these two words are going to be a part of the formula. We're never going to put the amount of solvent as a part of the formula. And of course, the volume of solution will be considered in the standard units of decimeter cube. Okay, that's how easy it is. That's how the units tend to be gram per decimeter cube for mass concentration. Okay. On the other hand, we have the standard type. I have no idea why it converts my M into a triangle. Okay, molar concentration. . Now, mole concentration is the unit that you're going to use most. If you look up a past whole decade of papers, questions related to quantitative chemistry or this chapter, you're going to find out that molar concentration questions are in there way too much, almost with every paper, every year, every season. But mass concentration really has about 2 3 questions in past 10 years papers. So that really tells about the rarity of mass concentration questions. Mass concentration is more like a unit that we used to deal with in past times a lot, but mole concentration is really the more standardized unit nowadays. So as the name suggests, the units are going to be mole per decimeter cube. And since molar concentration is something that we work with most, it's going to be moles of solute. And of course, the units are going to be mole itself over volume of solution. And again, the volume of solution is considered in the standard units of decimeter cube. Now, this gives us the idea that we might need to go for another formula to complete this formula itself. Since the numerator is moles of solute, that means we might need to work with the mole formula first and then put it over here. Yeah, that's true. That's why sometimes we expand this formula, and this formula can also be given as mass of solute, and that is in grams over mR of solute, that is in gram per mole, multiplied by volume of solution. And this time I'm going to change the solution volume units into cubic centimeter because this is the most appropriate units we work in lab with. In lab, since we do not handle with big amounts like decimeter cube, so most of the time we are actually working with centimeter cube. Uh, as an example, you may take up many pieces of apparatuses such as beakers or flasks or pipettes or burettes, and whenever you're going to look at the markings or measurements on top of them, they're all going to be in centimeter cube. So that's why this is the unit we deal with most. Over 1,000. Remember the conversion? We did the same thing almost yesterday, that if we divide it by 1,000, that's how we would be able to convert it into decimeter cube. So you can either use the contracted formula or you can use the expanded formula. It's entirely up to you. Both ways, you're going to end up at the same set of units mole per decimeter cube. I hope that makes sense. No.
Yes, sir.
Okay, I'm gonna. Okay, so interconversion, a question that we have faced before. Interconversion means to convert one kind of concentration units into another. Now, this is very much possible that they give you mass concentrated units and you might need to multiply and not multiply, convert them into mole concentration units, or vice versa may also occur. So this is the kind of questions that has been a part of past papers, so we really need to prepare our students for it. That's why the interconversion formula. So if you have mass concentration in gram per decimeter cube, and if you divide it by the MR of solute, which is usually given in gram per mole, you would get the units for mole concentration, which are mole per decimeter cube. That's how we convert them. Or you may rearrange the equation. You may multiply molar concentration with MR to give you mass concentration. It's really up to you. That's how this works. Clear enough? Now, what I'm going to do is that I'm going to start with very easy questions. Remember the easier questions we started off with when we were doing moles, just to convert moles into mass or mass into moles? That's how easily we are going to start with mass concentration or molar concentration questions. Then there would be some interconversion questions. Once you're capable of doing the easier concentration questions, it would automatically make you capable of doing the more difficult ones. So let's start off with some easier questions, and then we're going to move to the difficult ones. Okay. Let's start with some very basic concentration questions. Find out the concentration of solute in both mass concentration, which is stated in gram per decimeter cube, and molar concentration, which is stated in mole per decimeter cube units. So part one, I'm going to put up one part, but a single part has to be converted into mass concentration units and mole concentration units. What am I going to deal in? I'm simply going to tell you what the mass of the solute was used or what was the volume of the whole solution. So it would be easier for you to convert it into both units. Okay, I'm going to do the first question as an example for you. So 4 grams of NaOH in 100 cubic centimeter solution. Okay, so if that's the question, how are you going to work it in for mass concentration? First off, mass concentration. It's pretty easy. You actually take the mass and you take it in the units of grams. You put up the volume. The volume has to be in decimeter cube. So it's really easy. 4 grams of it. And remember, since it's 100 cubic centimeter, you divide it by 1,000 to convert it into decimeter cube unit. So that's how it works. And it's going to be 0.1. So the answer would be 40 gram per decimeter cube. Clear enough? It's pretty easy. Take the mass, put it as numerator, take the volume, put it as denominator, but you need to take the standardized units. So if there are any conversions required, you may do the conversions as a prerequisite. Move on with the question, you get your answer. Okay, let's move on to molar concentration, which is the more standardized unit. Now, let me tell you, even if they don't use the word molar along with the word concentration in papers, the single word concentration itself means that they are talking about the standardized type. So concentration word means molar concentration, all right? So remember this specific key for the exams. So it's pretty simple. Moles within their own units up top as numerator, volume as denominator. Okay, so how do we get moles? Moles are really mass over molar mass. So I can actually use the expanded formula. That would be even better for me because in that way I can use mass in grams and the volume in decimeter cube. Okay, so that's how I'm going to do it. I'm not going to use the shorter formula. So it's 40 grams. So my bad, it's not 40, it's actually 4. So 4 grams, and the MR of NaOH, since it's NaOH, Na is 23, O is 16, H is 1 in periodic table, the total is going to be 40. You may check it with the help of calculator. So it's 40 gram per mole, and I'm going to multiply it 1000 over 100 cubic centimeter. Okay, so 100, 100, this 0, this 0, this 0, this 0. This really is 1 mole per decimeter cube. Now, this is all of mental math. You may pick these numbers with the help of calculator, but I am pretty sure that you're going to land on the same answer. Okay, I hope this makes sense. But I've made a small mistake in there, which might be a little bit confusing for you. So I'm going to correct it. It's actually centimeter cube. That's not decimeter cube. Go through it. Let me know if you think you understand it. Okay. However, even if you're facing a little bit of difficulty, trying the questions yourself is going to make it more clear for you. Do you agree?
Yes, sir.
So do you find it easy? At least I guess you're going to find math concentration really easy, since it's a single step question.
I guess I could do a question, sir.
Sure. Then let me write the second question, which you are going to solve all by yourselves. So question number 2. Remember, along with the calculator, you might need a copy of periodic table with you. So
I guess just a second. I'll bring my per table.
sure, take your time. I can wait. And during that time, I'm going to write the question for you. It's 5.6 grams of KOH in 250 cubic centimeter solution. There you go. Take your time. Your answer, please. And is that for mass concentration or molar concentration? Because I didn't get it.
Sir, it's 22.4 grams slash decimeter cube. For
Okay, yeah, then that means it's definitely mass concentration. And if you have done it like this, you actually took 5.6 and then you took 250 divided by 1000 like this, or maybe 5.6 multiplied by 4 at the end. If you convert it, it becomes 4. So yeah, I guess you're right. It's around 24 point something. So your answer exactly was 24 point.
24. Sorry, it's 22.4.
Oh, 22.4. Yeah, that seems right. 22.4 gram per decimeter cube. Yeah, that's right.
1, because that's what I'm getting.
1?
Yes, sir, 1.
Okay, so you took 5.6 and over 56 multiplied it by 1000 over 250. That shouldn't be 1.
Yeah, I made a mistake, sir. What I did was 5.6 divided by 22.4, because yeah, I kind of got confused on that.
Okay, it's KOH, so it's the MR for KOH, and I'm gonna do it separately. K is 39 in periodic table, O is 16, H is 1. So I guess the total would be 56, if I'm right. So, okay.
Yes, sir. Yeah.
So you already have the next question. The formula is CH3COONA. It's carbon, it's hydrogen, it's oxygen, and it's sodium. It's actually a salt. It's not an acid or an alkali. So there you go. Take your time. The good part about this question, actually the easier part, is that you don't need any cubic centimeter conversion because the question is already given in decimeter cube.
Yes.
Take your time. So this time, if you have that picture in front of you in which we had concentration interconversion formula, it's going to help you, okay? Because I'm only going to give you 2 questions. We don't need to practice them more, since in the past decade, they have only considered a few questions, hardly 2 to 3 questions about these. You should only be capable of knowing how to convert mass into molar or vice versa, molar into mass concentration. That's about it. So if you understand how to do that, this really serves the purpose for the interconversion question. Okay.
It's done. Isn't it done by just switching the values? Because we'll just use the mole formula and just switch the values,
No,
right?
actually, we use the MR. If we divide the mass concentration by MR, we get the molar concentration. And if we multiply the molar concentration by MR, we get the mass concentration. That's how it goes. It's really the involvement of the MR of fluid. That's about it.
Okay. All right.
Okay. So question number 1, 10 grams per decimeter. So that's about it. You already have the formula, so it should be easy. Just calculate the MR of NaOH or KOH, which you might have already done in the previous one. So this should be easy. Take your time.